In this video, we're going to discuss electronegativity. So this is a property that exists for atoms all the time, but it's especially important in covalent bonds. Electronegativity is basically how much an atom wants electrons. So it's the strength with how much it attracts electrons. Now we care about the atoms that react, so we're not going to really look at the noble gases for this one. As you move to the right on the periodic table, you are more electronegative. Over on the left, you are less electronegative. So within a row, say lithium to fluorine, fluorine is way more electronegative than lithium. Fluorine wants electrons a lot, lithium not so much. Within a column, as you move up the periodic table, you are more electronegative, and as you move down, you are less electronegative. So if we look at the halides here, fluorine is the most up and the most right. It is the most electronegative element of all of our reactive elements. As I go down the column, chlorine it's far to the right, but it's not quite as up. So it's a little less electronegative. Bromine, again, it's farther right, but it's not that far up. So it's a little bit less. Iodine's a little bit less. As we go across, fluorine, oxygen, nitrogen, carbon. Oxygen's a little less electronegative. It wants electrons a little less than fluorine does. Nitrogen, a little less than oxygen. Carbon, a little less than nitrogen. There's a diagonal trend. The more up and right you are, the more you want electrons. Now there's arbitrary values for these. You can find them on page 391 in the book, or just hit Wikipedia for electronegativity. They have a chart. For things like fluorine is rated at 4.0. Oxygen's 3.5, nitrogen's 3.0, carbon's 2.5. As we go down, chlorine ranges between 3.0 and 3.5 depending on the book. Bromine goes down from there. These values have no specific meaning. They are a comparative unit only. But they provide us with a very handy tool for determining if a bond is fairly equal or if it's lopsided. When we think about two atoms, say a carbon and a carbon, and we draw the orbitals kind of around them, well, they really kind of average out. And you can treat them kind of as this average of the two spheres. You get this nice long oval around both atoms. If they're equivalent atoms, they pull on those electrons equally, and so the average of all the orbitals and electrons is spread equally over both atoms. But if you have something like carbon to fluorine, fluorine is a lot more electronegative. It really wants the electrons more. It pulls them towards it. The net result is that the electron average, when you overlap to share, is actually unbalanced. It leans very heavily towards the fluorine. So imagine you have a balloon and you squeeze one side, and it kind of pushes everything to the other side. This is more or less what's happening. The electrons are a volume in their orbitals, and so they shift to put more of their volume around the more electronegative atom. The result of this, well, if this was taken to the extreme, if you had a sodium and a fluorine, the electron would just completely hop over and it would be a full negative and a full positive. If you've partially done this, then you have a partial delta negative and a partial delta positive. The electron is in the process of being fully stolen, but it never gets there. Carbon does fight hard enough to hold on to its electron. Sodium, way over on the left, has like a 1.0, somewhere in the vicinity of about 1.0 for its electronegativity. As a result, it doesn't hold on very well. It's way over on the left. It's just very weak at holding electrons, and it doesn't. It makes an ion. But carbon is close enough to fluorine that it hangs on. This leads us to recognize a few types. We have an ionic bond on bottom. We have a covalent here in the middle. And the carbon and fluorine are covalent, but they have charge. Like poles on a magnet, a plus and a minus end. It is a polar covalent. Polar covalent bonds are covalent bonds that permanently have some charge. They are not ionic, so they still share electrons to one specific atom, but they do have actual charges in regions of space like ions do. They're just weaker charges. This has some practical effects, though. When you have things like water, oxygen to hydrogen, I'll tell you that hydrogen is 2.1 and oxygen was 3.5. Difference there is 1.4. The oxygen actually wants those electrons a lot more, and we often draw that by showing the bond with an arrow going one direction, kind of a plus sign on the other. What this represents is that the electrons are moving towards the oxygen. So the oxygen is going to be reasonably negative, and each of those hydrogens is going to be reasonably positive. We kind of average this out, and water really looks like it has a somewhat positive half and a somewhat negative half. Well, if you ever had a bunch of little magnets and you threw them together, they stick together or repel. Like they interact because they have charge. Waters tend to arrange themselves to favor those charges. And so that somewhat negative and that somewhat positive here will be drawn towards each other. This is an intermolecular bond. Intermolecular bonds work to keep molecules together. Why is a solid? Because the molecules are holding on to each other very tightly. Why is a liquid? Because they're holding on to each other reasonably tightly, but enough to still twist and flow around each other. And a gas is a gas because it's broken all of its attractive forces to other molecules. Polar covalents have much stronger interactions than purely covalent bonds. Your carbons and your hydrogens are actually fairly close in value. Your carbon was 2.5, your hydrogen is 2.1. A carbon and a hydrogen are effectively equally sharing. And for that, we have some ranges. If you are 0 through less than 0.5, you're covalent. If you are 0.5 through about 1.7, you are polar covalent. And these are the differences in electronegativity. And if you are greater than about 1.7, you are ionic. Now these are not hard and fast. These are rough values. They generally hold true, but hydrogen and fluorine do make a polar covalent bond, but they're actually different by 1.9. Hydrogen is a little bit of an exception, as it always tends to be. It can get physically closer than other atoms can, and so it can force a covalent bond even when most things would lose their electron. But our sodium and our fluorine were different by 3.0, and so they would fall into the ionic realm. Same with sodium and chloride, they're different by 2.5-ish, and so they fall into the ionic realm. Carbon and hydrogen are close enough that they fall into the just pure covalent. the neutral. And any equivalent atoms, dioxygen, dinitrogen, difluorine, they're neutral. They don't have poles. There's no polar covalent aspect to them. And so fluorine gas, F2, is a gas. Despite being really electronegative because it's fighting another fluorine, the two molecules don't look like they have any charge. There's nothing really to hold them to the next molecule. Whereas something that weighs significantly less, like water, is absolutely liquid at the same temperatures, simply because it can be attracted through those charges to a neighboring molecule. So having polar covalence changes physical properties. And in later chapters, those have gone into much more detail. For here, though, it's recognizing that the differences in our electronegativity affect the distribution of electrons. They shape the orbitals of the molecule in order to skew electrons to one side or the other. This has the practical purpose of creating charge differences that can attract different molecules to each other. Also explains why we tend to see anions from elements in the upper right. Oxides, fluorides, chlorides, bromides, sulfides, nitrides. Why is the upper right always anionic? Because they really want electrons. They're really good at acquiring them, and so they tend to pick them up and have extras. Why are things way over on the left cationic? Well, because they're really bad at holding on to electrons. If there's nothing trying to steal it, they can hold on to it, but as soon as an element from anywhere else drifts by, it'll steal the electron, because the other elements want those electrons more. And so electronegativity can help us understand why these standard monoatomic anion charges form the way they do. Atoms that want electrons more are just more likely to be negative. Atoms that don't hold on to electrons as well are more likely to be positive.